Welcome to solverfy.
Okay, so in this problem we have a sphere, a charged sphere. We're asked to find the electric field and electric potential everywhere in all the different regions. And we are assuming that the charge density increases as the square of radius inside the sphere up to some r naught radius of the sphere. So this is going to be a big Gauss's law problem to find the electric fields. And using the electric field, we can take an integral to get the electric potential. We can make use of the fact that we actually know what the E field of a charged sphere is. We know that E is equal to 1 over 4 pi epsilon naught q over r squared in the radial direction. We also know that V of a charged sphere is 1 over 4 pi epsilon naught q over r. However, we don't know what big Q is exactly, and we're going to have to deal with the inside of the sphere a little bit differently. So we can start with the outside because that's probably the easiest. So when we're considering r greater than or equal to r naught, we know that E is going to be q over 4 pi epsilon naught r squared, 1 over r squared. We need to find what Q is. So to find Q, we have to integrate over the entire sphere using this radially changing charge density. We're going to be doing something like this. Which will come out to be, we're going to be integrating mainly in r from 0 to r naught of kr squared. The integral in both other directions, in the theta and phi directions, will just yield 4 pi r squared dr. This would be this is actually 3 integrals in spherical coordinates, but 2 of them are trivial. What's not trivial is remaining here, but it's really just a polynomial, so we can do that. We'll end up with 4/5 k pi r naught to the 5th. Thus, k is equal to 5 big Q 4 pi r naught to the 5th. Okay. So returning to our E field outside the sphere, we have something like E equals Q or actually, because we're given Q. All right, we're given Q, but we have K. We've now figured out what this K has to be. So I guess this expression here is the electric field outside in its entirety, assuming we know what Q actually is. So to get the voltage in this outer region, we have to integrate from infinity, assuming that V equals 0 at infinity. That's usually our reference point. We're going to do the integral from infinity to some radius r outside of our E field, q over 4 pi epsilon naught r squared dr, which is not that bad of an integral. We'll end up with q over 4 pi epsilon naught r evaluated from infinity to r. The infinity part simply is 0 because 1 over r, where r is infinity, is 0. We are left with the result q over 4 pi epsilon naught r, which is not unexpected. So far everything is normal, nothing too spectacular. E looks like that of a charged sphere with some charge Q. So does the potential. It's inside the sphere where things will get a little bit interesting. So now let's start focusing on the inside. We found what the K constant is, so that'll allow us to actually get some real results. So doing Gauss's law, E dot dA, the integral, the surface integral, will be equal to the charge enclosed over epsilon naught. That's Gauss's law, of course. Since we have spherical symmetry, this integral will be something more like E 4 pi r squared, so just the area of that surface at some arbitrary r inside the sphere, be equal to charge enclosed. And remember, the charge enclosed for these smaller surfaces is going to be our electric charge density, dV, from 0 to r for that particular subsphere, all over epsilon naught. So the hard part is going to be doing this second integral inside the sphere. It's not too bad, though. First of all, we can isolate E, make this a little bit easier. We have 1 over 4 pi epsilon naught. This integral from 0 to r of kr squared. And we can plug in the k that we found earlier. 5q 4 pi r naught to the 5th. That's our k we found earlier. R squared 4 pi r squared dr. Where once again, this is a triple integral. This was a triple integral in spherical, but 2 of the integrals in the theta and phi directions result in a 4 pi r squared every time due to the spherical symmetry. We only really need to worry about the integration in the r direction. That's the non-trivial part. So if we are careful about how we do this integral, we do it correctly, we will end up with a result of 5q 4 pi r naught to the 5th times 4/5 pi r squared, which will simplify down a little bit more. Oh, you know what? Let's take a step back. Might be going a little bit too far. So let's include this piece. And that wasn't originally in front of the integral that I moved over the side. 1 over 4 pi epsilon naught r. Now times all that stuff. The result of the integral. 5q over 4 pi r naught to the 5. Times 4/5 pi r squared. So doing a little bit of simplification now, we should be able to get to the result of 1 over 4 pi epsilon naught r times q r to the 5th, r naught to the 5th. Finally, one more step of simplification. Q r cubed 4 pi epsilon naught r naught to the 5th. And that's it. And it's in the outward direction, r hat, if we wanted to add a direction to it. That's the electric field inside of a sphere for some arbitrary radius r. Last piece to do is to find V inside. So V of r inside the sphere is simply going to be V at the edge of the sphere, which we were able to find earlier, minus an integral going from r naught to r. With these kinds of problems, when you're finding the potential, you always work your way inwards because your reference point is at infinity, so you have to work your way inwards. All right. At this point, we can plug in our electric field for the integrand. QR cubed over 4 pi epsilon naught r naught to the 5th dr. This is a line integral going directly radially inward. We can pull out all the junk, all the constants. Actually, we can relatively straightforwardly do this integral. We will have this. All that evaluated from R naught to R. All right. And doing the last little bit of simplification, we have Q over 16 pi epsilon naught R naught times, in parentheses, 5 minus R to the 4th, R naught to the 4th. Okay, and that's it. That's the potential inside the sphere. So you can see that once you have a non-uniform charge densities, these problems can get a lot more difficult. You have to do a lot more integration, and it can be all around difficult. You have to separate out the different regions, but we are able to get all the different pieces. So what does this look like? So let's plot E first in radius. Here's our R naught. Here's E of R. So what this is going to be doing is it's going, ordinarily for a uniformly charged sphere, you have just inside the sphere, the electric field increases linearly rather. In this case, because we have something that's quadratic, we're going to have something that's not quite linear. It's going to be a little bit concave up. It's going to reach its maximum right at the edge of the sphere. And at that point, it's going to look just like a 1 over r squared dependent falling off electric field as usual. That's it. For electric potential, we have something kind of interesting. Maybe not. We will have an electric potential that's falling off as 1 over r, some maximum point, and then doing a slightly concave down, not quite level, concave down, but still slightly increasing potential up to the origin. And outside of it, it's going to be proportional to 1 over r. So that's it. We found the electric field and electric potential in all regions, inside and outside of the sphere. We used Gauss's law to find the electric field, both regions, and we used a line integral of the electric field to get the electric potential. And that's it.